Now today's class will be relatively short because the amount of work we did yesterday was quite large in terms of looking at concentrations, with the major concentrations being percentage WV, percentage WW, and then we moved from there into parts per million, and from parts per million into moles per litre. So I hope you've got on okay with those questions, because we are going to look at them tomorrow in the live class. But I just want to just finish this section in relation to concentrations, and I want to talk about a couple of things. First of all, dilutions. Now, obviously, when we in the lab order in hydrochloric acid or sulfuric acid or whatever, they come in at a very, very high concentration. Okay, now we don't use them like that. What we have to do, and sometimes you'll see me do it before an experiment, they have to dilute down the actual concentration of the acid before we can make it usable, okay, and use it in a given experiment. So to do that, we simply add water. Now, here's what I want you to think of. When we dilute something, we basically increase the space that's available between the particles of the acid, okay? So you take your concentrated acid, a very, very small amount, and then you add water. So you're increasing the space between those particular molecules, which makes it more dilute. It has nothing got to do with the number of moles. It has nothing got to do with the number of molecules. They're still going to be mathematically the same. It's the space that we give, it's the amount of solvent that we place into this particular solution that calls the solution, or causes it to change from being concentrated to dilute. So as we said already, most laboratory reagents are purchased at high concentrations and they have to be diluted. When a solution is diluted, the amount of solvent is increased. Now, look, the universal solvent is water, but in chemistry there are other solvents. So just keep in your head that yes, most times we're talking about water, but not all the time. We could be talking about cyclohexane, we could be talking about alcohol. There are other solvents out there. And here's what I want to show you. There's the liquid that's in high concentration. Now notice that the amount of space between these particular molecules is very, very small, okay? In order to dilute this particular acid, we add water. And what happens? The space between these particles is increased. So therefore, by adding water, you're giving more space to these particles, meaning that you end up with a dilute solution. But I do want you to look at the number of particles. And let's say, for example, that one blue dot is a mole. There's 1, 2, 3, 4, 5. There's 6 moles in this concentrated solution. There are still 6 moles in the dilute solution. So therefore, the number of moles is not affected. Okay, the physical presence of the acid remains the same. Whatever number of molecules you start with in the concentrated solution, that's the number of molecules you'll have in the dilute solution. Okay. But what does change is the concentration. It's how many of those molecules are present in 1 centimeter cubed of the solution. So when you're diluting a solution, the concentration changes, but the number of moles doesn't. Now, another way to say that would be as follows. 2 people in a bath is concentrated. 2 people in a swimming pool is dilute. Notice the number of people is the same. The only difference between the 2 solutions is the amount of water. 2 people in a bath, very little space. 2 people in a swimming pool, huge amount of space. Bath, concentrated, swimming pool, dilute. But the number of people doesn't change. And that's what I need you to think about when we're moving into this dilution section. So finally, then, as I told you already, imagine this diagram as having 6 moles in the first beaker of a concentrated solution. And then after adding water, we have 6 moles in a dilute solution. Okay? But the number of moles doesn't change. It's the amount of solvent that you add that does change. Okay, so in order to solve dilution problems, we're going to use a formula V1M1 equals V2M2. Now again, please remember, I always err on the side of leaving volume in litres, and I just do that. I don't think about anything else. I just keep volume in litres. It just makes life easy. Okay, keep it in litres. So you've got the volume of the first solution times its concentration, M means molarity, is equal to the volume of the second solution times its molarity. So in other words, if I just go back to the previous diagram we had there, if I multiply the number of moles by the volume, and in this one multiply the number of moles by the volume, I'll get the same answer. So the moles by the volume by the concentration here and the volume by the concentration there would be exactly the same. And that's what we're talking about in this particular formula. Okay, so here's an example. What volume of 12 molar HCl solution is required to make up 500 centimeters cubed of a 3 molar solution? Now, notice what you're doing. You're making up a solution from stock. Now the stock is usually the more concentrated one. So you're taking the 12 molar solution and you want to turn the 12 molar solution into a 3 molar solution. So what does the formula tell me to do? The formula says multiply the molarity by the corresponding volume. So let's read the question again. What volume, so that's going to be X, of a 12 molar, that's the concentration, is required to make up equals 500 centimeters cubed. Now please keep it in liters. So that's 0.5 liters of a 3 molar solution. And that's the second concentration. So in other words, you can see it there. It becomes 12 times X, because that's the first solution, the volume of 12 molar, equals 3 times 0.5. And all we've got to do then is simply engage with algebra and say that 3 by 0.5 over 12 is your answer. And taking your calculator, that comes out as 0.5 divided by 4, and 0.5 divided by 4 is 0.125. Now, what are we looking for? What volume? Liters. And if they ask you for the volume in centimeters cubed, there's 1,000 centimeters cubed in a liter, so it's 125 centimeters cubed. Okay, now I have that typed in there for you, so I'll just remove that handwriting and I'll go through the steps and show you what we did already. So using the formula, you take the volume and the molarity of the first solution. There they are. It's an unknown volume with 12 moles, 12 molar solution, and you set it equal to the volume times the molarity of the diluted solution. And there it is there. So it's going to be X times 12 equals 0.5 times 3. And by a simple rearrangement of terms, dividing both sides by 12, like that there, we end up getting X is equal to 0.125 litres, or 125 centimetres cubed. Okay, another example. A student takes 15 centimetres cubed of a 2 molar nitric acid solution and dilutes it to 250 centimeters cubed in a volumetric flask. What is the new concentration of the acid? Now, when we're diluting it, when we're making up a solution, call it whatever you want. If we're diluting it, then here's what we know. The volume times the molarity here is equal to the volume times the molarity. Well, there's the volume, and they're asking me for the new concentration, which in this case will be X. So V1M1 equals V2M2. Now, what's the volume and what's the molarity of the undiluted solution? Well, it's 15 centimeters cubed. Now, 15 centimeters cubed in liters, you divide it by 1,000, it comes out as 0.015. So that's the volume in liters, multiplied by its corresponding concentration, which is 2, is equal to 250 centimeters cubed. That's 0.25 of a litre, multiplied by an unknown concentration, which is X. And again, all we've got to do is divide both sides by 0.25 in order to get X on its own. Like that. That cancels with that one there. And X comes out as, and again, always have your trusty calculator nearby, 0.033, because it's 0.015 multiplied by 2, divided by 0.25, and that comes out as 0.12. Now, 0.12 what? What are they asking me for? They're asking me for the new concentration. So 0.12 molar, or if you want, moles per litre. I don't mind which way you write it down. Capital M or M stroke L, they're both exactly the same. Okay, so I'm going to leave you with something to do. I'm going to, that's written there as well, so let me just take off the handwriting. So there you go. V1M1 V2M2 get exactly the same answer. You're going to try these two now, so I'm going to ask you to pause this video now, try these two, and again we'll take them up in the live class on Friday. So when we are working with solutions, when we're diluting solutions or making up solutions, okay, there are specific solutions in chemistry that we have to begin certain processes with. You can't just make up a solution willy-nilly and not know what you're dissolving and how much of a substance you're dissolving in water or in any other solvent. A standard solution is one in the lab whose concentration is known. So you'll often see written, you'll see labels sometimes like this in the lab, and it'll have 0.5 molar HCl. Okay. Now, if I know what the concentration of a solution is, then it's a standard solution. So if anybody was to ask you, what's the definition for a standard solution? Simple. A standard solution is a solution whose concentration is known. Now, what about all the other concentrations that aren't known? Well, we can work them out by titration once we involve a standard solution. So every time we do a titration, one of the solutions have to have a known concentration. And put it another way, one of the solutions must be standard. We must know what its concentration is before we actually use it. Okay. So a standard solution, that's the definition, is one whose concentration is known. We make a standard solution by dissolving a definite amount of solute in a suitable solvent, which is usually water. Now, when I talk about a definite amount, the reason why it's a definite amount brings us back to the chapter on the mole. Because if we have a definite mass of a certain substance, then we have a definite number of moles. And if we put that definite number of moles and make it up to a litre solution, that is the concentration of the solution in moles per litre. So you take the grams, you turn the grams into moles, you make the moles up to 1 litre, and the concentration will be that number of moles per litre. That's its molarity. So it is that simple. But there's a problem, as I said before, sometimes a litre is wasteful. Okay, and then we don't make up a litre, we make up 250 centimetres cubed or 100 centimetres cubed or 500 or whatever the case may be. But just keep at the back of your mind that the reason why we need a definite amount of matter to dissolve in water is so that the definite amount of matter contains a definite amount of moles. So we know the number of moles that are going into the solvent. All standard solutions are made from what's called a primary standard. Now, again, we can't just make a solution up from any old substance, okay? In order to make a standard solution, the actual solid that we begin with has to have certain characteristics. You can't just choose any solid from the presses in the lab or the what you call them, the benches inside in the prep room. You can't just take them. There are only certain substances that we can use that will allow us to make up a standard solution. Okay, and in order to make a standard solution, we have to begin with a solid. That's what we call a primary standard. Now, in order to qualify as a primary standard, the solid we're using has to have at least the following 3 characteristics. Number 1, the solid must be available in a very, very high form of purity. It must be very, very pure. Okay. Number 2, it must be extremely stable in air. So when you take the lid off or you put it out on a little clock glass or a weighing boat, that it's not going to interact with the oxygen, or it's not going to absorb moisture from the atmosphere, or it's not going to desiccate and dry out on you. Okay, it has to be very, very stable in air. And thirdly, not only does it have to be pure, not only does it have to be stable, it has to dissolve well in water. So at a basic set of characteristics, take those 3. What is a primary standard? It's a solid who's pure, stable, and dissolves well in water. And only the solids that are pure, that are stable in air, and dissolve well in water can be classified as primary standards. And primary standards are the solids that we use to make standard solutions. Okay, so think of it that way. A primary standard, which is a solid, is used in order to make a standard solution. And then the standard solution is used in order to work out what the concentration of non-standardized solutions are going to be. So that's why you start off always with something pure, stable, and soluble. They're the 3 brand marks, if you will, of a primary standard. So it's normally a solid. You then take a certain amount, or as it says here, a definite amount, and you take a number of moles, and you make up your standard solution. And that concentration will be known. And once you've got the concentration, say 1.5 molar, well then you can use that in titration with other substances whose concentration is not known. And by a very simple calculation, the concentration of the unknown solution will be revealed. Okay, now I want you to just take a look at this diagram here. Look at this picture over here. This is sodium hydrogen carbonate, if you can see the print up there at the top. Is this a primary standard? Well, first of all, let's check and see how pure it is. It gives a list of all the impurities, okay? And down here then at the bottom it says that you can expect the purity to be between 99.7 and 100.3%. Now don't worry about going over the 100%. I know you're saying 100% is everything, but that's just their way of letting you know it's extremely pure. So it qualifies on the purity. Secondly, does sodium hydrogen carbonate dissolve in water? And the answer is yes, extremely well. And thirdly, do you see any hazard symbols? Do you see the oxidation symbol or the harmful symbol? No. And there's no water in this molecule. So it is pure, it is stable, and it's soluble. So therefore we would classify sodium hydrogen carbonate as being a primary standard, from which I can make a standard solution, from which I can titrate then and reveal the unknown concentrations of other solutions. So a primary standard, as we already said, and again this is a definition, so there's two things you need to remember. That's your first definition there, and this is your second definition. A primary standard is a solid with the following three traits. Number one, stable in air. Number two, extremely pure. And number three, very, very soluble. So once we have a primary standard, how do I make a standard solution? Now, is it a case that I weigh out a definite amount, a definite mass? The answer is yes. Okay, so you start off with your primary standard, which is a solid, and you weigh out a definite mass, because in the definite mass there are definite moles. Now, what do we do with those? We dissolve them in water or in this whatever solvent we're going to use, and that then will give us our solution. Okay, and if we make it up to 1 litre, well then it will be a standard solution, because we'll actually know what it is in moles per litre. It'll be that number of moles in 1 litre of water, which will give me the concentration. Okay, now again, we don't do this particular preparation like the way we would prepare a cup of tea. You slap on the kettle, you throw in a tea bag, you throw in a drop of hot water, you put in a spoon of sugar, you don't count the crystals, and then you put in a drop of old milk. What's wrong with that? We don't know the quantities. You don't know the quantity of milk, you don't know the quantity of water, you don't know the quantity of sugar. That's kitchen chemistry, okay? Stay away from this. Because we're dealing with primary standards and standard solutions, there is a very, very set way to prepare a standard solution. And this is it. And I'm going to go through the steps with you now. I don't know if you can make sense of this diagram over here, but this diagram tells me what to do. And I'm just going to follow it with you. Number one, you take your definite mass of primary standard and you dissolve it in water, making sure that it's all dissolved completely. Okay. You then transfer the solution into a volumetric flask through a funnel. And the reason for that is because we want to make sure that we transfer all of this solution into this volumetric flask. Okay. Now, every single time you transfer something, please rinse the beaker. Look, third thing is you then rinse the beaker and you transfer the washings also into the volumetric flask. And the fourth thing we do then is extremely carefully, we keep on adding what we call deionized water until we reach the mark that is on the neck of the volumetric flask. Okay. Now, the video goes into an awful lot more detail, and I'm going to let you watch the video yourselves. The video tells you exactly and very pedantically how to make a standard solution. And I do want you to watch it, because there are phrases and terms and things in there that I can't show you here that they're going to be able to show you. But just to take the steps out again. I don't want them. Thank you. Okay, so let's just take the steps again. Number one, if I wanted to make up a 2.5 molar solution of NaCl, what would I do? Well, first of all, is NaCl available pure? Yes. Is NaCl stable in air? Yes. Is NaCl dissolvable in water? Yes. So therefore, it is a primary standard. Okay. Now, I want to make up a 2.5 molar solution of the following. Okay, of NaCl. So what do I do? First of all, and listen to this carefully, I weigh out 2.5 moles of NaCl. Now, how do I weigh out moles? And this is what I need you to remember. Can I weigh out moles? Yes, I can. What I've got to do is turn the moles to grams first, remembering that NaCl, sodium, is 23 and Cl is 35.5. So therefore, the mass of NaCl is 58.5 grams. So what I'm going to do, if I want 2.5 moles, is I'm going to multiply it by 58.5 grams by the 2.5 to tell me that I have to weigh out 146.25 grams. Now, let me just get rid of all the rest there. So that's what I need to weigh out, because inside that 146.25 grams of NaCl will be 2.5 moles. Once I have weighed out my 2.5 moles, what do? Well, come on. I dissolve the 2.5 moles, which is 146.25 grams, into 100 centimeters cubed of water in a beaker. So we're down here. Okay, I dissolve it in water there. Once I've dissolved it, I transfer this solution, number 2, into the volumetric flask through a funnel. I then rinse the beaker and transfer the washings. Now I'd say do that about 3 times. Okay, just rinse the beaker. You don't have to go mad, copious amounts of water. Just rinse the beaker and transfer the washings carefully also into the volumetric flask. Then make the solution up to 1 litre. Now, on the neck of the flask, there's a mark like this, okay? And that mark tells you exactly where you are to fill water to. But there's a problem. When you put water into glass, it doesn't go in a straight line. It kind of goes in a U shape like that. That's called the meniscus. C-U-S, okay? It's called the meniscus. And in order for me to make sure that the meniscus of the water is in the perfect place, here's what we say. We keep adding in water drop by drop until the meniscus sits on the mark. So when you look at that at eye level, the meniscus has to sit bang on that mark that is etched on the side of the volumetric flask. So when we say carefully make up the solution to 1 litre, we mean keep adding water down here, keep adding water drop by drop by drop until the meniscus, which is the U shape of the water, sits on top of the mark. Now, not that it holds on, we don't want it like this, that's wrong. If you do it that way, you're wrong. It has to be up sitting on that mark on the neck. And once it sits on the mark of the neck, then you know that you've put in exactly the right amount of water. And the last thing to do, once you've done that, is to stopper it and to invert the solution. Now, some people say, how many times should I invert? I would say between 15 and 20 times. And the reason for that is to make sure that all the solute has been distributed equally through all the solvent, and so that your solution is homogeneous. That's a very important word. Homogeneous. And homogeneous just simply means that it has the same molarity from the very beginning right down to the very end, that you've distributed the solute throughout the entire solvent. That's scant in its detail. I need you to watch that video, and I need you to watch it 2 or 3 times, get used to the language, but also to try and identify exactly how to fill your volumetric flask. What does the meniscus look like? How do I get the meniscus to sit on the mark? They'll show you in the video, so make sure you watch that. Okay, and now that we've finished, so I'm going to stop here. I told you it was going to be a short little class. I want you to watch the video as I said already, but I also want you to tackle the questions that are here. All right, now I know we've got a lot of questions banked up from previous classes that I want to take into class on Friday, and we will do that. But work your way down through 13.8, 13.9 and 13.10. Those 3, by the way, they're all dilution questions. Okay, so they're dilutions. And then 13.11 is just asking you 4 simple questions on the video that you've watched. Various different steps along the procedure of making up what we call a standard solution from a primary standard.